All right, so yesterday we did a little bit of practice on naming of ionic and molecular compounds, okay, and that seemed to go pretty well. We'll have a little bit of time here and there over the next week to practice that, but for the most part, we're not going to be spending a lot more time on naming because it's mostly review from Science 9. I did post yesterday in Google Classroom the solutions for all of the worksheets from the worksheet booklet on naming, right? So you can check those out if you're wanting to kind of work through some of those. But know that we will have a little bit of class time to work on those worksheets as we go along. And then we talked about the expectations for a proper lab report, right? And so what we're going to go over today is the stuff that's going to help you with the lab we're going to do next week. The lab we're going to do next week is going to work like this. There are going to be like a dozen unknown compounds on the front table. You will have to use their physical properties to identify them. Okay? So they're unknown to you. Their possible identities will be listed, but you'll have to figure out, okay, sample A is ethanol, sample B is sodium chloride, sample C is nickel 2 chloride, and sample F is water. Okay, like you'll have to use their physical properties to determine their identity. So you'll have a list of here's the identities, but you got to match them up. Everyone kind of follow what I mean there? Okay, so what we're going to go over today are some of the physical properties and behaviors of ionic and molecular compounds that will help you to do that next week. Okay, I know some of you are thinking right now and going, that seems really daunting. Like, I'm basically just going to be guessing. No, you won't. Okay, there's going to be some that are so obvious, okay, as to what they are. That basically just by looking at them, you'll know which one it is. Okay, and then you might have to do a little bit of process of elimination to get the last couple. Right, but in general, it's not too tough to figure out which is which. So key points for today, we need to learn the properties of compounds. That would be acids, bases, ionic, molecular, okay, all of that kind of stuff, okay, and understand how those properties can be used to identify a compound, which will be useful when we design our procedure on Monday. Right, so you're actually going to have to write out the procedure for this lab. It's the only lab we do where you have to do that, but I'm basically going to walk you through it and say, here are the 5 tests you need to run. You just need to basically write instructions on how to run them, which I will tell you, and you can basically just write them down. It's pretty easy. 5 easy marks on your lab report if you follow instructions carefully. Yeah, questions so far? All right, so all matter has certain properties. Matter has physical properties and chemical properties. We're going to be focused on physical properties, okay, today and for this first lab. Right? Physical properties are the things about a material that are readily observable or evident without anything else around. Okay, I don't have to mix it with anything to find these properties. The properties I'd have to find out by mixing it with something else are its chemical properties, right? Because that involves a reaction with something. So chemical properties are, okay, the chemical properties of this is it's highly reactive in water. I wouldn't know that unless I put it in water, okay? So for example, sodium is a soft silvery metal. Doesn't look like much to just look at it, well, except that it's usually stored in a container of kerosene. Because if it comes into contact with even the water vapor in the air, it reacts violently, okay? But you don't know that to look at it, okay? It just looks like a soft silvery metal. Okay, if I threw it in a bucket of water, it would blow up. I don't know that by looking at it. Okay. Similarly, if we had no experience with TNT, for example, I mean, like everyone sees a stick of dynamite and they immediately go, "Ooh, that looks dangerous," because we have an association with that. Okay, but if you were to just look at the chemical that goes into dynamite, it doesn't look terribly dangerous. Okay, gasoline, you can't smell it. You don't have any associated, it's clear liquid, and it doesn't look terribly dangerous. As soon as we get the smell, we know what it is, okay? But those are physical properties, okay? Its smell is a physical property. Its appearance, its state, those are all physical properties, okay? But as soon as I get a lit match near it, suddenly I find its chemical properties, okay? But that's gonna change it. Once I find out its chemical properties, it is no longer going to be that material, because in a reaction, atoms can be separated, joined, rearranged, and they make new materials. Not new elements, but new materials. Okay? So the physical properties that we're looking at, these are things that are just evident about that material by itself. So they would be, like we said, smell, okay, state, melting point, boiling points, solubility, okay, whether it dissolves easily, color, taste, but we're not going to do that, okay, because that's dangerous. Okay, stuff like that. Those are all physical properties, okay, things that are readily observable. Okay, density, also something that's readily observable, right? If I pick up, you know, a piece of styrofoam and a chunk of iron, one's definitely more dense than the other. Okay, it's just a physical property. All right, so those properties can be used to distinguish between different types of compounds and then individual compounds after that. All right, so ionic compounds, typically, and by typically we mean like 99% of them, okay, are crystalline solids, or salts, at room temperature. So the whole idea of calling table salt salt is partially true. Salt is an ionic compound. But salt is a general term for any crystalline solid ionic compound. Okay? So technically any crystalline solid, okay, that is an ionic compound would be a salt or a type of salt. Doesn't mean all of them would be good on your food. Right? Lead 2 chloride is a salt. I wouldn't put it on my food. Okay? I don't want lead poisoning. It's a salt. Probably doesn't taste very good. It's yellow. Okay? But you know, you can put all kinds of salts on food that are safe. Okay? Anything that's an ionic compound is technically a salt. Okay? They have very high melting points. That's not something we're going to test in the lab because we really don't have the ability to get things up to 600 or 700 degrees in order to watch them melt. Okay? So they're going to be crystalline solids at room temperature because of that. Ionic compounds will also, we discussed this before, conduct electricity when in solution. Okay? Don't think you could take like 2 electrical leads and put them in the salt shaker and have it conduct electricity. The salt itself doesn't. Okay? It's not charged when it's in its solid form. But if you dissolve it in water, okay, we talked about how it breaks up into the charged particles or ions, the negatively charged non-metal ion, the positively charged metal ion. Okay, now that solution will conduct electricity. Whereas if I dissolve sugar in water, it doesn't break up into charged particles and the solution will not conduct electricity. Spoiler alert, that one will be important for your lab. One of your unknowns is table salt and one of them is sugar. They look a lot alike. And you can't taste them to find out which is which. But sugar's molecular and doesn't conduct electricity in solution. Salt is ionic and does. All right, so what we're looking at here, guys, okay, if you looked at any ionic compound under a microscope, they would have a defined or a characteristic crystalline shape. Okay? All ionic compounds are crystalline, but their crystals are all a little bit different. So if you really knew what you were looking for, you'd actually be able to identify a lot of them based on the shape of their crystals. And some of them are brightly colored, which we'll get into in a little bit. Okay? When we dissolve something in water, an ionic compound that is, okay, then we get this breaking up into positively charged ions, negatively charged ions, and that solution can then conduct electricity. All right. Questions there? All right, so super important to have this, okay, highlighted. Because that's going to be one of the tests that we're going to run in the lab, okay? An aqueous conductivity test. That is, we'll make a solution with all of our unknowns, not all together in the same solution, each in a separate solution, okay? And test the conductivity. If it conducts electricity, then you know that it is not any of the molecular compounds on the list. Okay? You can immediately eliminate things like water and alcohol and stuff like that. Well, although you can eliminate those two because they're liquids. Okay. Now, lots of ionic compounds also produce brightly colored solutions. So copper compounds are typically blue. So if you have copper 2 chloride or copper 2 sulfate or copper nitrate or anything like that, okay, those salts are typically going to be blue crystalline solids, and when you put them in solution, the solution takes on the blue color. Okay, so if you've got a blue crystalline solid and it conducts electricity in solution, you've got something that contains copper, right? And that would be one of the things we would want to use to help identify stuff on Monday. Or sorry, on Tuesday when we do the lab. Okay, so if I'm looking at something and it's a blue crystalline solid and I've only got one unknown on my list that has copper in it, that's probably it. Okay, that's that kind of easy process of elimination that we can use to identify some of the compounds. All right, nickel compounds are typically green. Okay, so if we have a green crystalline solid and its solution turns green and it conducts electricity, and we got something on our list that contains nickel, that's probably it. That's what we want to do. Cobalt-containing compounds can be anywhere from blood red to faded orange. Okay, typically their solutions end up being kind of pinkish. Okay, so the solids can be, like I say, dark, kind of blood red, okay, to faded orange, but typically when you put them in solution, they turn pink. Lead-containing compounds, not that you have any, typically make yellow solids. Okay, I don't have that listed here because none of your unknowns will have lead in it. All right, questions there? So would those colors be something you'd want to have highlighted?
Yep.
Definitely, okay, because that's going to help you identify unknown compounds for your lab. All right, now molecular compounds. Oh, sorry. Al?
Are we still going to do a test next Tuesday, or are we going to
Oh,
do
yeah.
the lab instead?
No, we'll still have a quiz. It'll be a short one, be a few naming questions, and we'll be done. Okay, so molecular compounds can be solids, liquids, or gases at room temperature. Okay, they can be anything, solid, liquid, or gas, because they typically have low melting points. All right, so think of like carbon dioxide. Okay, carbon dioxide is a gas at room temperature. In fact, its melting point is, or sorry, its boiling point is what, minus 40 or something like that. Okay, you've ever had dry ice? Anyone seen dry ice before? Right. You don't ever see carbon dioxide in its liquid state. It sublimates directly from solid dry ice to gas, to carbon dioxide gas. That's how they make smoke in smoke machines and stuff. They have dry ice. Okay. So you have that, or water. Another example, low melting point, so liquid at room temperature. Okay, but evaporates and boils at 100 degrees Celsius. That's actually pretty low as a boiling point. Yeah, so typically you've got those things. Butter, okay, would be another one. Right? Melt, you can melt in your hand. Coconut oil, the same thing. Okay, it's a molecular compound, low melting point, it'll melt in your hand, and stuff like that. All right, molecular compounds are not usually as soluble. There are exceptions, like sugar is highly soluble. Okay, but most molecular compounds are not as soluble. So if you're mixing something and it's just not dissolving, it's likely to be an ionic compound. Now, is that going to be a definite thing? No, but it can help you. Okay? It can help you on the right track towards it. The big thing is that molecular compounds, when in solution, so if they do dissolve, their solutions do not conduct electricity because they do not break up into those positive and negatively charged ions. So if I have a glass of distilled water and I put a conductivity tester in there, it'll show 0. If I pour alcohol in there, it'll still read 0 because alcohol is soluble in water, okay? And it's a molecular compound, so it doesn't conduct electricity. Now, what if, and I say what if because this will happen, one of our unknowns is water and one is alcohol. How will I tell them apart?
Color?
No, this is not, I'm not pouring rye, okay? Like, I mean, like, this is like lab grade ethanol, okay? It's pure ethanol. Don't drink it, okay? It tastes really bad, okay? But it also what? Smells. It smells like hand sanitizer, okay? And that's the active ingredient in hand sanitizer is alcohol. Okay, so you're going to have a way to separate them because every other behavior, every other physical property that we're going to test for alcohol and water is going to be the same. Okay, they're both liquids, they're both clear. They both will dissolve easily in water. Water obviously dissolves in itself, but alcohol dissolves in water as well. Okay, their solutions will both not be conductive because they're both molecular, right? Their only difference is one smells and the other doesn't. Hopefully the water doesn't smell. If water smells, don't drink it. Okay, general rule. Okay, making sense? So that's what we want to go through. It's not going to be like super tricky. Okay, like you're going to be like, oh man, I've got 12 things, I have no idea what any of them are. Okay, you're going to be able to tell what probably half of them are right off the hop. Okay, it'll be that easy. Okay, molecular compounds which are soluble in water typically produce clear solutions. You don't have a lot of brightly colored molecular compounds. Okay? Typically it's the metals that make the bright colors. Okay? So you're typically going to get clear solutions if you get something that's soluble in water. Like pour alcohol in water, stays clear. Dissolve sugar in water, it gets a little cloudy maybe, but it stays clear. Okay? No brightly colored stuff. All right. In this lab, you are going to have one unknown compound that is a strong acid. And you are going to have one compound that is going to be a strong base. And by strong, I mean the acid will have a pH of 1 and the base will have a pH of 14. Okay? They are as strong as either one can be. That's why we have to be very careful with all of our unknown solutions, because you don't know when you'll be picking up the two that could, burn off your skin. Okay?
That's nice.
Yes. I like to mix things uber concentrated because, you know what, I want the results to be clear when you do something. Okay? I'm not one of those, I'll make it 0.1 moles per liter. Not 12 moles per liter. Then I know. Okay? I'm going to pour it right out of the sample jar, okay, and it'll be good. So, things to look for acids. Okay? Strong acids are ionic compounds. Okay? All strong acids are ionic compounds, and they all have hydrogen acting as the metal. Okay? So they all have H plus ions in them. They are ionic compounds, hydrogen acting as the metal. They dissociate, that is, come apart very easily. That's what makes them acidic. The hydrogens are freed very easily when put in solution. Okay. What makes acids strong or stronger, okay, is the number of hydrogen ions that they can donate. So this, barely do that, is hydrochloric acid. It's what's in your stomach digesting your food. It's a strong acid. In your stomach, it has a pH of about 2, okay? But you can have it very strong and okay, have its pH be much lower than that, right? But it's a strong acid, but how many hydrogens can it give up? How many hydrogens are in that compound? 1. So it can only give up 1 hydrogen, okay? Whereas this stuff can give up 2, okay? It's a stronger acid, because it can give up more hydrogens. This stuff is even stronger. Okay? The reason this stuff is stronger, okay, is because it dissociates more easily than hydrogen sulfate. Hydrogen sulfide dissociates more easily, so it can become a stronger acid. Okay? This is a gas that you have to be careful of if you're in oil and gas, because it can be an associated gas coming out of wells. So if you ever have talked to someone who works on a rig, they always have to take a course about H2S safety, because if you inhale that, it will dissolve the inside of your lungs. Okay? So it can be quite dangerous. And then you could have something like this. Nitric acid. Okay? You don't even want to get the vapor from this on you. You'll be blistered in hours if you just get the vapor on. Okay? In fact, with all acids, you have to be careful about their vapors. Okay? I've had this happen where I was mixing some acids and diluting them, and I sneezed just as I was pre-COVID. Okay? Just as I was having the acid, the concentrated acid bottle open. What do you do right after you sneeze? Inhale, yeah, sharply, right over the acid bottle. Okay? Yeah, just like pouring blood. Okay? Like, yeah, it's bad. Okay? You don't want to inhale any of those things. So, if we're smelling an unknown compound, lab safety-wise, how do we do it?
You fan
You
it.
waft it. You don't go over and go, okay? You're not doing lines of stuff here, okay? Like, you just need to get a hint of the smell, right? Because, I only say that because I've had people that come over like, you can't smell it, Coder. And then they're like, I'm like, yeah, I told you not to do that. Okay? Now you're gonna like smell vinegar for a week because most acids smell kind of vinegar-like, okay? Because vinegar is an acid, okay? So they have kind of that sharp smell to them, okay? And that sharp vinegar-like smell. So that's what you're gonna want to waft, okay? If you smell that kind of vinegar-like sharp smell when you're wafting at arm's length, okay? Because remember, I'm gonna make these really strong, okay? You'll be able to, it'll be a good indicator that it's an acid. All right, now this we're not gonna try. Okay. They taste sour or tart because, well, that's true. I mean, lemon juice is a weak acid. Vinegar is tart. Okay, but we don't want to be tasting any of the unknown compounds in here, or it will be the last thing you taste as it dissolves your tongue and teeth. I can walk around my face. Okay, you don't want that. Okay. So we don't want to taste anything, okay, because that's dangerous. Now, acidic solutions will have a low pH, okay, that is less than 7. And one of the tests we're going to run is the litmus test. Okay, we'll put the Hydrion paper, which gives us a reading from 1 to 14 by its color, in each solution and get a pH reading. Most of our compounds are going to be somewhere between like 4 and 8, okay, or 4 and 9 even. Okay, but they're all going to be around neutral. Okay, we're only going to have 2 extremes. Okay, one really strong acid, one really strong base. So if I've got one unknown compound and it's an ionic compound that starts with hydrogen, it's probably going to be what? Acidic. Yeah, it's going to have a low pH. Okay, it's going to turn the litmus paper red. That's another thing to look for. Okay, you're only going to have one compound that's going to do that. All right, questions on that? Okay, so they are typically crystalline solids because they are ionic compounds. We, however, cannot purchase them or have them shipped in their solid form. Okay, it's just like a transportation safety thing. You cannot even have these things in their solid form. So they are shipped to us already in solution. So one of the unknowns, I will tell you, okay, on lab day, this stuff is a white crystalline solid, but it's already in solution. Kind of be ridiculous with it. It's the acid, but okay, you still run the tests on. All right. For bases, strong bases are also ionic compounds, but they all have hydroxide ions in them. Okay, so OHs. So this stuff is a strong base, sodium hydroxide. It dissociates very easily. Okay? It's what's an oven cleaner. Okay? The stuff that dissolves crud off the inside of your oven is a very strong base. And they are just as corrosive as strong acids. All right? So they are ionic compounds. So if you've got an ionic compound that ends in OH, it's probably going to be a strong base. Okay. Is that a strong base? Yep. Is that an ionic compound? What does it start with? Carbon. So it's molecular, is it not? Right? That's not an ionic compound. It ends in OH, but it's neither basic nor is it an ionic compound. That's ethanol. That's stuff that's in hand sanitizer. C2H5OH, it's alcohol. Right? It is not a strong base. Everybody with me there? All right. Now, these are, because they're ionic, they're going to be like acids. They're going to be some of your best conductors of electricity. They dissociate very easily. So they have lots of free positive and negative ions when they're in solution. So they're going to conduct electricity very well. They're going to have a very high pH, okay, so higher than 7. And they are typically not going to have any like smell per se. They all smell a little bit different. There's not really a basic smell except maybe earthy. Okay. but they would be bitter. Okay, so if your parents ever washed out your mouth with soap, okay, soap is made from lye, which contains sodium hydroxide, okay, and so would taste bitter, okay, very, very bitter. So anything that tastes bitter is typically a base, right? Baking soda would be another example. If you ever tasted baking soda, it tastes very bitter. All right, questions on bases? All right, so that's all we need for the properties and stuff. I'm going to talk a little bit about our lab design and some of the tests that we're going to run. So this stuff you'll need to write down because it isn't in your notes package. All right, so we'll have these unknown compounds at the front, and I'll show you the equipment that we're going to use on Monday when we're actually talking about designing the lab, okay? But you're going to have what's called a depression plate, okay? It's called the depression plate not because it's sad, okay, but because it is got these little pits in it that you can put stuff in, depressions, okay, little depressions on it. So we're going to put the unknown compounds in these depressions, and then the first test that we want to perform is the observable properties test, okay? And it's just like it sounds. You just want to record as much as you can observe by just looking at it, okay? What are the things that are readily observable about this particular compound? So what would be some things we'd be looking for?
Color.
Color. What else? Shape, yeah. Is it crystalline or is it like waxy, okay, stuff like that? What else?
Whether it conducts electricity or not.
That'll be one that we'll test after because I have to alter them to do that, right? It's their solution that conducts electricity.
The state that they're in.
State, solid, liquid, or gas. If it's a liquid, I know right away it's not an ionic compound, and I can eliminate more than half of the unknowns from the list as a possible identity. Okay? What else?
Texture.
Texture.
Smell.
Smell, okay? All of these are the things that are readily observable to you, okay, right off the bat. And we want to do that test first because all the tests that follow are going to alter it slightly, okay? So we have to do this test before we do anything else to the compounds. So we got our observable properties test, and these are the things that we want to look for, okay? We want to look for color, look for the state, okay? Look for the nature of the matter, crystalline, cloudy, okay? Stuff like that. Do an odor test by wafting. Okay? That will tell you the observable properties.
Like the crystal source ones, but instead of the purple ones that turn your fingers around and stuff, would those be considered a salt as well?
Yep. It's potassium permanganate, right? Metal, non-metal, metal, polyatomic ion. So yeah, it's definitely a salt. Okay, so that's what we want to look for the simplest test, or the first test. Okay, just observable properties, write down everything we can get. Because we know that some of those observable properties are going to be really important in the identification of the compound. Okay, state's one that's really important, and color is one that's really important. Okay, odor, it'll help with like one of them, right? But the rest, pretty much are all the same. They don't really have a smell. Okay, but all of those things are going to be important. Okay, so we want to have them recorded. The next thing we want to do is record whether or not this material is soluble or not. Okay, so how do we test solubility? What do we have to add to all of them?
Water.
Exactly. Okay, so we're going to take some water and we're going to add it to the depressions and give it a stir, okay, and see what happens. When we stir it, we also want to record any temperature changes that occur. Okay? And the reason for that is some ionic compounds, especially acids and bases, increase in temperature when they dissolve in water. Okay? In fact, you have to be really careful when you're diluting solutions that are acid or base. Okay? They can get really hot, and they can get hot really fast, so much so that they can actually break the glass of the container you're pouring into. So you always add acid to water and never the other way around. Water has a very high heat capacity, so if you pour acid into water, the temperature doesn't change as much. But if you go the other way, the acid does not have a high heat capacity. It heats up very quickly, so much so that the glass can't expand fast enough and it can shatter. Okay? So you have to be very careful with those. That's not going to be a problem for us because the depression plates are either ceramic or plastic. Okay? So you don't have to worry. Plus, there's not enough of anything there for that to happen. Okay? And there's going to be one compound that will get colder when you add water to it. Okay? So I'm going to give you a bit of a tip here because this one would be hard to identify otherwise. Okay? But this stuff what would that be called? What's NH4? That special polyatomic ion. Ammonium, and what's NO3? Nitrate. Ammonium nitrate. How many people have ever used one of those cold packs where you pop the little ladder full of water and then you shake it up and it gets cold? Okay, if you use one of those, you have used ammonium nitrate. Ammonium nitrate is the little crystals you can hear rattling around inside of that thing. When they dissolve in water, the solution gets colder. It's an endothermic change, okay, and so it absorbs energy from the surroundings, gets colder, okay, so that one there during the solubility test is one to watch for, okay, whichever one of your unknown solutions gets colder, okay, would be that one. Okay, so that's our second test, solubility, okay, basically we just want to see if it dissolves. How do we know if it dissolves? Will it all disappear? Does it all have to disappear for it to be soluble? Not really. The amount, like you're going to put, the stuff in these small depressions. You're never going to be able to add enough water for most of them, even the really, really soluble ones, to dissolve. Okay, because there's just not going to be that much water in there. So what you got to watch for are things like if the crystals are colored, does the water take on the color? If it does, they're dissolving and they're soluble. Okay? You need to look at the shape of the crystals. Are they changing? Are they getting rounder and softer, okay, as a result of you putting the water in there? Any temperature change indicates that dissolving is going on. Okay? Yeah, things like that is what you have to look for. If something separates and floats on top, it's not soluble. Okay, like oil and water, for example. Oil's not soluble in water, it will float to the top. Okay, so any sign that the other material is disappearing into the other. Can one liquid be soluble in another liquid?
Yes.
Yes. Okay. If I pour alcohol into water, it just disappears. Okay, and I just get one clear solution. Okay. If I pour, let's say, coconut oil into water, they're both clear if the coconut oil is in its liquid form. Okay, and they'll float on the top. Okay, that means it's not soluble. So you're going to have to look if there's any separation, okay, if they're liquids, if you're putting liquids into each other. All right. So color change, are there any new odors that are happening? Okay, typically that's an indication of a chemical reaction, but it's something to watch for. Right? And then, once we've made the solutions, and we've recorded whether everything is soluble or not, then we want to test the conductivity of the solution. So it's important to do these tests in order, because each one alters the stuff as you go along. Okay? So, we perform the solubility test, the conductivity test after the solubility test. The conductivity test is really easy. We have these little conductivity meters, They have a little button on them and 2 metal leads. You put the 2 metal leads in the solution, push the button, and record whatever the number on the face is. Okay, they go from 0 to 10. Okay, so your non-conductive solutions would typically be 4 or less. Okay, there's always going to be some small amount of conductivity, okay, unless you've got something really pure. And then anything that's like 6 or higher would be highly conductive. And you're going to get some that are going to be 10, okay? But you'll get a lot that are like 8, 7, 8. Those are conductive. Also really important to make sure you rinse everything in between tests. Okay, we said for the solubility test that we're going to be stirring them, we're going to be using a thermometer. That needs to be rinsed between each test. If I don't do that, it could contaminate the next sample with the first one. Okay, so I don't want to do that, so we would just rinse them off. We'll have a little wash bottle, squeeze it and squirts out distilled water, and you can wash off both the thermometer, the stirring rod, and the conductivity tester between tests. Okay. Once I've done the conductivity test, I have 1 test left. Okay, and I have to do this one last because it will chemically alter the solution. And that test is the pH test. Once I stick litmus paper, okay, into the material, it changes it chemically. It's a chemical reaction because there's a color change. Okay, so the pH test, just place the pH strip in the solution, and then you compare it to the little color chart on the bottle.
For the conductivity, it's just like look for lights.
Yeah, look for lights. There's a light bar that goes up, and it goes from 0 to 10. So you just count the lights.
Okay, so the more conductivity is, the
The more lights will light up. Yeah. Okay, so those are the 4 tests that we'll run. And from those 4 tests, we'll be able to identify the unknowns. Okay? Each one will have a slightly different set of data, okay, that is unique to it. Okay, questions on that? That's good there. All right, so you're going to have an observations chart that will already be in your lab report template. Okay, you'll build it, or it'll already be there. Okay, but you'll need to print it. And we can do this, like you can do this on Monday or whatever. Okay, because you're not going to take the Chromebooks across the hall on Tuesday to the lab. Okay, we don't do that. So to record your observations, if you want, you can record them right in the chart from your phone. That's fine if you want to do that. But maybe you just want to have it on paper and transfer it after, so you don't have to have your phone out, or it could, get acid on it. That would be bad. All right. So questions on any of this stuff here? Okay, I'm going to put a couple of naming questions up on the board here. Naming and formula questions, so we can practice that a little bit. Okay, give those ones a try and we'll go through them before the bell goes. Okay, so our first one here, okay, is this ionic or molecular? It's ionic. Beryllium is a metal, so this will be beryllium fluoride. Okay, and our second one, we've got molybdenum, which is a metal, with oxygen. But molybdenum has more than one possible charge. Okay, so we need to figure out which charge it is. Okay, oxygen's always a -2. There are 2 oxygens, so that's 4 negatives. So this must be the molybdenum with the 4+ charge. Okay,
Artemis is a 6 place.
that's all it says?
Yeah.
Weird, because mine here clearly says 6, 5, 4, 3, 2.
Ours just says 6.
Okay, they must have changed that recently. Okay, that would be confusing for you, since you don't have a 4 on there. Okay, what's going on? All right. Okay, for the next one here, we've got phosphorus and nitrogen, ionic or molecular? Molecular. So this will be triphosphorus dinitride, right? Remember, we got to end it in I. Okay, and this one here, ionic or molecular? It's molecular, both nonmetals, dicarbon, hexahydride. Okay. All right, for these 3 here, we got to write the proper formulas. Okay, copper 2 sulfate, that's the Cu with the 2+ charge. It's with sulfate, which is -2, CuSO4. Okay, remember the Roman numeral tells us the charge. Trinitrogen, tetrabromide, N3Br4. Okay, we just use the prefixes. Lithium carbonate, lithium's a +1. Carbonate is a -2. Drop and swap. We don't need brackets on that one because the 2 applies to the lithium and not the carbonates. Ringing a bell? Sorry, I know I went through that kind of fast. We're running out of time. Okay, have yourselves a good weekend, but not too good.